All right. Welcome everyone to our CISL seminar. We have two presenters today. They're both coming to us from Princeton University. And we have Josko Plazonic and Jonathan Halverson. They will be speaking on job monitoring and efficient GPU cluster utilization with Jobstats. I do want to say shout out to Prentice Bisbal for recommending these presenters, and I'll put a link in the chat if you have a recommendation for a future speaker. Take it away, Jonathan and Yasko.
Thank you, Virginia. And again, thank you, Prentice, for arranging this. So Jasper and I will tell you about some things that we've been doing over about the last 3 or 4 years to get the most out of our hardware. And we'd like you, if you want to interrupt at any time, feel free to unmute and let us know what your thoughts are. So why job monitoring? Here are some typical reasons. And number one for us is that GPUs are very expensive and they're very much in demand. And so a lot can be gained by tracking their usage. At a university, we've got a range of experience levels, and we have like literally maybe like 1,000 people are just learning HPC as they go, and they're sure to waste resources. And then we have experts that have been doing things for decades, but you can still make mistakes, and without any monitoring or tracking, it's mistakes that can last for years. Oftentimes things go wrong with HPC jobs, and if you're doing monitoring, then you have a wealth of data and you can try to troubleshoot more easily. And then the last thing we'll mention is that as you make changes to the cluster, you may discover performance degradation. And by having data over a period of a few years, you'll be able to identify those things. So there's a few other reasons, but I think those are essentially the main ones. So again, for us, it's largely about GPUs, and we all know about the increasing cost of GPUs and the increasing demand, and just how it's hard to even get them. So a lot of what we're going to talk about today is how do you get the most out of your hardware without spending any money, because most places just don't have several $1,000,000 to spend and get a substantial amount of new GPUs. Typical examples of wasting resources. These are both real world. The first one is showing an instance of what we call multi-node CPU fragmentation. So this is probably a beginner, and instead of allocating 96 CPU cores on one node, they allocated 96 nodes and one CPU core per node. And they did that for 2 hours. And so, of course, any job trying to use all the cores on a node while this was running on those 96 nodes was completely prevented. And then another common thing we see is people installing software which is CPU only and doesn't have the GPU libraries. And you can, of course, still allocate the GPU, but the code simply can't use it. And so you wind up wasting GPUs in that way. And we'll look at about a dozen other ways that people bring about underutilization. Okay, so our remedy for this is something called Jobstats, and this is something that Josko got going a few years ago, and I'll let him talk about the design.
So fundamentally, what we are interested in is collecting as much data as possible, and then tagging that with job IDs so that we can then organize it and get some useful data out of it and act on it. So what we do is we run a couple of different exporters to collect the data with Prometheus. So we run, your typical node exporter that's used to collect the basic stats about the node, CPU frequencies, NFS utilization, overall node memory use, and InfiniBand stats, for example, are one of those that are pretty interesting to have, and a ton of others. Then the obligatory next exporter that we use to collect data about jobs is the cgroups exporter, which is a modified version of a cgroup exporter written by Trey from OSC that will enrich that data with the job ID, task, in the case of Slurm, also task and the step. That collects the CPU utilization and the memory usage on that particular job and its various steps. Then for the GPU nodes, we also run NVIDIA NVML-based exporter that collects your basic stats, like the GPU utilization, the memory utilization, and in the newer version, we also have some of the newer stats via GPM extension that allows us to collect also SM utilization, FP16, FP32, and a bunch of others. We combine that with a post and pre with a prologue script so NVIDIA Exporter is also enhanced to collect additional data, which we drop on a node with a prologue script that allows us to connect the job that's running with the GPU that they're using. And therefore, now we have also an ability to connect the two and calculate what's the utilization of that GPU job and act on it. We can also take advantage of some of the other exporter, like the GPF exporter, but that's that's not used in the actual calculation of any job efficiencies. But we find it useful to collect that data as well so we can look at the overall utilization of the job in a Grafana dashboard and see how the job was performing as far as its network file system use, which is also especially useful when one of the things that John mentioned is that how the past data can be useful, and that's one of the ways that it can be useful when people complain, hey, my job used to run this fast, now it doesn't. We can look at all of that and connect, look at the old job, look at the new job, and see what's different. Anyway, then from that data that we all store in Prometheus database, we can combine that and produce, usually what we do in our case is that at the end of a job in the Slurm epilogue, in SlurmCTLD epilogue, we will calculate a summary of those results. Essentially, it's a JSON summary that contains overall job efficiency and like GPU efficiency per node, CPU efficiency per node, and a bunch of other basic stat memory, of course. And we compress that and store in one of the fields in the Slurm database. As an alternative, one of the contributors has also added the ability to store the same data in external database in case one has a problem with storing this in the Slurm database. We use Slurm's admin comment field to do this. We, base64 encode it, compress it a bit so it doesn't consume as much space. And that gives us an overall summary of the job, which is very useful when we run reports that can be across many thousands of jobs to see how people have been using the cluster or how someone's efficiency has evolved over time. Some of the researchers on campus actually, and IT people on campus, have written extensions, their own code, to help their lab members analyze their job performance over time as well. We also use the same data that we store in the Prometheus database to present present a dashboard that John wrote, a simple command line dashboard that presents the GPU utilization across the cluster to help users submit their jobs and to be aware, to see how many GPUs are free and also to see theirs if they're efficient or not. The Jobstats command itself is a command line tool that can either look at if the job has already finished, it can do the quick thing and retrieve the job summary out of the comment field in the Slurm database and present that result. Or if the job is still actively running, it can show the current job utilization by talking directly to the Prometheus database, fetching all the numbers, running the queries, and formatting them in a easily readable output. And then we have all these, we have Job Defense Shield, which is something that John has spent a lot of time perfecting, that can use all of this data to act on our behalf and do things like send reporting emails to the user or to the sponsor or it can even act when it notices that like GPU jobs are not doing things efficiently or not doing it at all. Either warn them or maybe even terminate jobs if that's what the steering committee decides to do. And then we have utilization reports, as I mentioned, that a lot of that we have and others have written for this. Do you want to move on to the next one?
Should we? Does anyone have any questions about the design? Looks like Prentice and Ben.
Yeah, I see report Ceph. Is that different than the old Ceph command?
Yes. Report stuff, it's specifically designed for array jobs. So it will show you the utilization for all the elements of the array in one shot. So
Right,
it'll
thanks.
use stuff if it doesn't find job stats, but if you're a job stats site, then it'll use the job stats data.
Okay, thanks.
I would say one of the things we found very useful in a different context is GPU node power. Do you have access to that in your current stack, or?
Absolutely. That's
Yeah.
one of the basic, GPU power, the temperatures, all of that is a basic NVML stat that can be collected, that is collected. Of course, that's not as useful in the calculating efficiency of a job or something, but all of these things can come in very useful. Like for a while, occasionally we have a problem where, people complain that a job is slow. Then you look at you look at the job details of that particular node, and you find out maybe that in the case of GPU job, that power utilization never goes up too high. Then maybe you find out that the node is overheating, and that's why, or maybe that one of the power supplies has gone dead. And that helps point you out towards that conclusion. We've had occasionally unexplained slowdowns with the CPUs where they throttle down. I mean, it's not like some of this can be caught differently, so usually, hopefully your monitoring would catch if a power supply goes down. But we've had cases of machines shipping with barely attached CPU coolers, and suddenly they will start throttling, and you don't know why. And you can find that out by looking at the detailed stats and see that the CPU frequencies of that particular node are just not going up, staying very low. So yes, we collect that and far more.
Excellent, thanks.
Okay, we can come back to this, but I think we'll go on.
So the way that this is usually configured on a brand new cluster, as far as at least is in particular in the case of Slurm, is that we need Slurm can account for utilization either through the classical so-called Linux utilization, where it looks at each individual process and tries to see who its parents are and so on. But for this to function properly, we need that to be switched to be using C group-based GPU counting. It's not only because it's easier for us to collect, but also because the other one is flaky. It does not detect when process is detached from parent, and when the process PID1 becomes their parent. Then the next step is to set up all of the required exporters. The C group exporter, we have our version, even though I'm working with the OSC folks to try to port some of the changes to their original C group exporter. So our version of the exporter for the relevant version of the operating system, because V1 is different from V2 as far as these things go, obviously. Node exporter, while not strictly necessary for the functionality of Jobstat itself and the job efficiency, it is extremely good to have. If you find out, for example, that you have slow MPI jobs or erroring out, it's good to find out that you have IB errors, and that's one of the things they will show, one of the many things that it collects, or that maybe a job is using too much NFS instead of a faster GPFS file system or similar better performing file system. GPU exporter, that's NVIDIA GPU exporter that we have also on my GitHub site. And GPFS is optional, but we like having in the case of GPFS stats for that. so that we can tell how, if a job is using it efficiently, if they're using maybe too many small IOPS, too many small job IO requests for the large ones, or they're not. Anyway, for that, then for the GPU, as I mentioned already, we require a couple of small prologue and epilogue scripts to help us determine which actual GPU is being used by a job. That speeds up. We're actually pretty concerned about efficiency, and this, while one could find this out differently, you could look at the list of all the NVML allows some of that, allows you to look at the PIDs of processes using the GPU, and then you could try to see which process that belongs to, and so on and so forth. But it's much more efficient and less intrusive on the system to, at the beginning of a job, to note down exactly which GPUs it's using, and we note that down in a /run directory. We use the GPU GUID as the file name, and we store in there which job ID is using the GPU and which user is using it. And then and the NVIDIA exporter is modified to collect that as part of the job and returns it to be used to connect it to calculate stats. Then Prometheus server obviously needs to be configured to collect all of this data from all of the nodes. And finally, for the Slurm, we have a epilogue script for slurmctl epilogue script. This is a script that runs at the end of each job. And we use that opportunity to calculate the summary and store it in the admin comment in the Slurm database for easier and much faster calculating of the summaries of the job. Finally, if you have open on demand, I mean, this can be used, Grafana can be used, of course, without open on demand, but we have a small mini open on demand app that queries the database and then produces the appropriate URL for the Grafana dashboard to display the relevant jobs. So it makes it easy for people to find the stats for that particular job. There's also another mini app that can show you the summary of your recent jobs. So obviously, we have so far only done this for Slurm and for the NVIDIA GPUs. As far as the GPUs go, we just didn't have many AMDs yet, actually just a single one. But it has worked. It works on all generations of the NVIDIA GPUs, except that the additional stuff, the GPM-based stuff, which allows you to get more insight into what kind of operations your job is actually running. If you're using a lot of FP jobs, FP floating point calculations, or is it doing a lot of SMs or whatever it's doing, that extension, and also the GPM also allows you to look into utilization of individual MIGs, which the old one cannot on its own. NVML on its own cannot do that without the GPM extension. So this, I should mention, that only works on H100s and newer. So we actually don't have a good insight into MIG utilization on A100s. It's a limitation on the NVML platform. And we're aware that DCGM-based exporter can do some of that, but it's much more intrusive and it conflicts with use of GPUs with, if you want to run your own debugging and tracing with DCGM, you couldn't do that if you had also our exporter running with DCGM. So while we explored that, we switched back to using the GPM enhanced NVML and the GPU exporter. So these are actually, John knows this better than I do. These are some of the sites that have started using this. I think all of them are using the basic functionality. And John, some of them actually started using the enhanced one. They started stopping jobs or notifying people and summarizing, right?
Yeah, that's right. We'll see that soon.
All right. Well,
okay, we'll go on to a live demo of Jobstats. So I'm just on a terminal, and what I can do is run the Jobstats command, and then we'll pick a job ID. And so we'll take one that has idle GPUs. And when we run this, it will show us the metadata at the top. And so typical things like job ID and which partition it ran in. And then in the middle is the overall utilization. And we try to do this text-based graphical bars to help people understand if the efficiency is good or not too good. And so you see red already for GPU utilization. And then the third section is the detailed utilization. And you can see it shows the values on a per node basis. And in the section for GPU utilization, you can see that there's red bold text indicating that the utilization for the GPUs was 0. So the hope is that a beginner would see that there's clearly something wrong. And if that isn't sufficient, then down at the bottom, there's a set of notes. And it's telling them that it didn't use any of the GPUs and that they should resolve this before running subsequent jobs. And then there's a link to our help page. Let's look at another example. This one will have a lot of problems with it. And so once again, you get metadata. And so this is a job that ran on our LLM cluster. And they took 6 GPUs. And we see that the overall utilization for the GPUs was 25%. And then it's showing the CPU utilization on a per node basis, as well as CPU memory usage. And then finally, the GPU utilization and the GPU memory usage. And then finally, lots of notes for this one. And so it's complaining that the job allocated almost a day and it only used 14% of that. And then it's saying that the GPU utilization is low. And it's pointing out that it's using 6 GPUs from 6 compute nodes. But the GPU nodes have 8 GPUs per node. So really, they should combine them together. And then they're using too many CPU cores per GPU. We want them to use up to 12. And then there's some other stuff. There's too much CPU memory and what are these? Yeah, too much memory per GPU and so on. So that's like the worst. That's typically you never see that many nodes, but this was a job which happens to capture all that. So let's look at the Grafana interface. So we'll grab a job that's running. Try this one. And then we'll run Jobstats on this. And then, so this one only has like basically no nodes. So everything's healthy for this one. And then at the bottom, we have this URL. And we can copy that. And then go to the web browser and then load it up. And so now we're seeing all of the Grafana data, which is through Prometheus. So you've got the CPU utilization, and then the memory usage, and then the GPU stats. So the utilization is very high. The memory usage is around 16 gigabytes. And then this is what Ben asked about before. We've got temperature and power. And then we have things on the per node level. And so this is the overall CPU utilization across all the cores. And then same thing for the total memory. So we do node sharing at Princeton. So the per node quantities, one has to keep in mind that you're sharing this. CPU frequencies, NFS stats, and the list goes on. There's more I/O. Here's the GPFS bandwidth that we talked about. You've got local disk IOPS, and then InfiniBand errors in the packet rate. So lots of quantities. You can zoom in on these and do all kinds of nice things to understand how your job is behaving. Any questions about the Jobstats command or the Grafana interface? Okay, we'll go on and look at, covered all this. Okay, so one thing that's nice is if you add in this --mail user, you put your email address in there, then when your job finishes, the output of the Jobstats command will be sent to you by email. And that will include the notes that we saw at the bottom, as well as the URL to the Grafana web interface. So people can quickly access all of that. And then as Josko mentioned about the summary statistics, when a job finishes, the data is in JSON format, and we base64 encode it, compress it, and then it gets stored into the admin comment field in the Slurm database. And so this way, if you run the Jobstats command on a completed job, it'll do a quick lookup because it's already done the queries and stored that already. And then after about a year, we have to get rid of the Prometheus data because we're sampling every 30 seconds. And in some cases, we're taking tens of quantities. And so it adds up. And so we expunge it after a year. Okay, we also have this on-demand helper app. And to see that, we go to our on-demand web interface and choose jobs. And then it will show us a list of the active jobs. And this will be everything, but we could filter it if we want. And then if we just pick one of these and scroll down, we get a quick overview of the CPU utilization and the CPU memory utilization. But one can also click on detailed metrics, and that will pull up the Grafana interface.
I should mention that this particular functionality comes for free if you do the things right according to Open on Demand. And we do. So this is pretty much by default. We didn't add too much to it. It's just we're doing it the right way.
And then just one more nice thing is you could enter a job ID if you have a job ID. So we'll take this one and then enter that in, and then you can get to the stats that way as well. Do you have any more comments on the helper app, Josko?
You might as well show the other one, what's it called? Can you go back to the jobs menu? The completed jobs app. So you may want to pick a user unless you have a lot of jobs. Hyen, he's an active one.
Good call.
Hyen. And you can also click on the, yep.
Yep. So instead of using the command line, you can go through the web interface.
But this obviously works only for completed jobs because it relies on the summary to present the data.
Okay, we saw the on-demand helper app. Okay, so let's move on and talk about auto cancellation. So this is something we've been doing for well over 2 years. And so here are some reasons to do it. Of course, the GPUs are very expensive, and so you want them to be used for jobs that actually use them. And by canceling immediately, the user knows that there's a problem. If you have people allowed to run for days, then they may come back in several days and find that there was an error and their results aren't waiting for them. So it's advantageous to just cancel immediately. And then they can also get upset because they wasted their resources, their fair share goes down. And so now subsequent jobs have to wait longer and they got nothing out of the idle GPU job. And then lastly, before we set all this up, when we would see a bad job, we would take the time to write a one-off email to the user, and it just takes more time than you think. And so it's really nice to do this in an automated way. So here's some numbers for one of our clusters. So if we weren't applying auto canceling, to our LLM cluster, which has 336 H100 GPUs, we would be losing 6% of the total GPU hours. And so this is over a 6-month period. We found that there were 151 users, and more than half of them had at least one job that had an idle GPU. And so I think that this is a particularly extreme case. Most of the CPU hours are associated with multi-GPU jobs. So when things go wrong, the effect is magnified. When we look at our general purpose GPU cluster, then the number's like 1%. So it's not as bad, but for all the reasons that I mentioned on the previous slide, to us, it really makes sense just to get the software set up and just have this all be eliminated.
But it's actually more than that. One of the things that we saw extremely frequently 2 to 3 years ago was people not installing their software correctly. They would install, as John pointed out sort of at the beginning, PyTorch, but the wrong one, the CPU version, and then they would run sometimes for months. And never, because they didn't know better, they would not know that this is running much slower than it should, and that the GPU is just sitting idle or unused. And even some of the modeling software that can use GPUs, people don't always compile correctly with the GPU support, and then they would run thinking they're using GPUs when they are not, and they're just being wasted. There's a lot of wastage that just ended, or the jobs that they would people run because, I ran a job with 1 core, I'm going to now allocate 5 nodes and expect that it will scale. Whether they even tried to run it across 5 nodes, or whether they were just using a single node and the 4 of them were sitting idle, all of that just gets caught automatically, and they usually learn pretty quickly. We don't get many tickets anymore about any of this. They get notified, and if they don't know how to fix it, they will contact us, but usually they fix it on their own. So there's a lot of wastage that's prevented out the gate with that, 52% of 151 use, that we don't even see. And it's probably a huge percentage of the cluster. Probably would be interesting if we had all the stats, and they would show much bigger savings than they're happening now, because people are getting better because of this help that we're providing.
To give you some insight into what the software takes for parameters, you set up a YAML file, and you specify the cluster name, and then the partitions that you want it to apply for. There's like your sampling period minutes. That's how frequently you run cron. And then finally, you can specify how many minutes should pass at 0% utilization for every measurement, which we do every 30 seconds, before they get the first warning, the second warning, and then lastly, the job just gets canceled. And so for this configuration, we're canceling after 90 minutes. And so that applies to the first 90 minutes. And then if the job did use the GPU during that period, but at a later time it stops, then we use a sliding window to catch those cases. And we cancel if we find that a job has been completely idle for 5 hours, which is pretty lenient. And then if you look at the last 2 lines, we're distinguishing between batch and interactive jobs. If an interactive job is ran and they only allocate 1 GPU and the runtime limit is 6 hours or less, then we completely ignore them. They don't have to use a GPU at all. But if they use more than 1 GPU, or if they ask for more than 6 hours, then they're subject to the same cancellation rules. When a user gets their job canceled, they get 2 warnings, and then they'll finally get this cancellation email. And it's just telling them that the job ran for 90 minutes at 0% utilization, and so it was canceled. Okay, we did a brief survey about a month ago, and these are all the sites that we found that are canceling. And 6 of them are using Jobstats with job defense fields, and then the others are using their own software. And so I'm hoping that this list grows. here are some of the software tools that people use to do the calculation. We talked about Job Defense Shield. There's a brand new tool coming out of George Mason called GPU Watch. It's going to basically debut at PERC, and you can see it's fairly sophisticated. There's a Python layer, it uses systemd, and then it uses Ansible. And it's just specifically for canceling GPU jobs and for keeping an eye on the performance. ASU has a tool called the HPC Dashboard, and currently they only can use it to cancel Jupyter notebooks, but they're planning on extending that to all batch jobs. And then lastly, it should be fairly straightforward to write some code to do this. And I know that Boston University has done this. They basically call NVIDIA SMI every 2 minutes, and they track that data, and then they cancel when they see. I think they use like 2 hours, a 2-hour window, and then they'll cancel. So there's a choice of tools out there for achieving this. Okay, so that's 0% GPU utilization, but what about all the other things that can go wrong? This is a list of the different instances of underutilization that our tool, that Job Defense Shield, can address. And so on the GPU side, we look at low GPU utilization. So this is non-zero, but what if you're running at 5%? Are you going to let somebody run at 5% utilization for 4 years? Then you've got people allocating too many cores, too much CPU memory. And then if you have a range of GPU models, sometimes they'll take the powerful one when they could have ran on the least powerful one. And then there's cases where they're doing like 1 GPU per node and splitting the job. And then they're requesting too much runtime. On the CPU side, it's similar quantities. The big one is over-allocating CPU memory. We want to track that closely. And then all the time we see people running serial codes, but they allocate multiple CPU cores. And so we can catch those cases as well. So before I present the numbers as to how many emails we're sending out and how much waste we're seeing, I just want to let everybody have a sense of what our systems look like. And so today we have 3 large systems. Dell is about 30,000 cores, and it has about 800 GPUs. Stellar is principally a CPU-only cluster. And then Tiger is, again, it's largely CPUs, 61,000 CPU cores, and then a small number of H100 and L40S. And we had 2,300 users on those systems in 2025. So here are our numbers for all the different instances of underutilization, as well as the number of emails that we sent and how many people received them. So for the GPU jobs with idle GPUs, we contacted 184 users in the last 6 months, over 2,000 emails. And depending on the cluster, we save between 1% and 6% of the GPU hours. You can see that roughly 200,000 GPU hours are associated with jobs that have low efficiency. And so on the general purpose cluster, I think we look at a utilization of less than 50%. And then on the LLM cluster, it's 75% or less. And you can see that the 200,000 is approximately 7% of the total GPU hours. The rest of these ones, they're not too bad, but every bit helps. So we keep running those alerts. GPU model too powerful. We're not really losing much there, but we still like to contact those people. And same thing for the multi-GPU fragmentation. It's not such a big loss. It's, I guess, just greater than 1%. On the CPU side, I don't know if this number means anything to you, but 27 petabyte hours of RAM that people allocated and didn't use. I can tell you that for sure that people were blocking CPU cores from being allocated because there wasn't enough memory available on those nodes. And so we do have a big problem with that, and we've been contacting all these people. And then, what is it, 6%, I think? Yeah, 6% of the total CPU hours is associated with jobs that had a low CPU efficiency. And we sent 127 emails to 53 people about that. And then serial allocating multiple cores, that's not too bad. We can deal with that. And then the CPU fragmentation, a bit more substantial. And so we sent roughly 200 emails concerning that. So when you sum it all up, we send 7,500 emails per year, which works out to about almost 3 1/3 per user per year. So on a per user basis, it's not bad at all. But there's a lot of activity. Any questions on underutilization? Prentice, please.
Yeah, got a couple. First of all, GPU model too powerful. What exactly do you mean by that? Are you talking about they're using like CUDA, they're using libraries that have like a lower CUDA capability than the one that they're actually running on so that they're not using all the features of that particular GPU?
I think I have it. Let me see if I have it on the next slide. Okay. No, that's not it. Well, it sort of is. Yes, you could do it by generation, but we do it by whether we've taken advantage of the multi-instance GPU or MIG. So we take some of the GPUs and we divide them up, making smaller GPUs, and we want people to run on those, but they wind up running on the full GPUs. And so we contact them and say, please run on those small GPUs. It's essentially what you're saying.
Gotcha. Okay. Now, the other thing I'm noticing on this table is that for the GPU at 0% utilization, there's a big discrepancy between the number of users and number of emails you sent out. Can you comment on that? Do you have any insight as to why that is?
All I can say is it's computer science people, and I think they're just firing. You can imagine using this system as a way to find out if you made a mistake without taking the time to see whether you made the mistake. And I almost think people are doing that. They quickly do things, and then they say, if I don't get an email in 30 minutes, I know it's okay. But it's a huge number, but I checked it, that's what it is.
Okay. Thank you.
Anybody have anything else? Okay, so if you're wondering what happens if they ignore the emails, fortunately, we have 3 policies in place where we can quickly suspend accounts. And we can do that for 0 GPU utilization, over-allocating CPU memory, and running serial codes using multiple CPU cores. And so we're supposed to send a warning to their PI, and then if they do it again, then we just block their account for a period of at least 7 days. Okay, let's talk about GPU fractionalization. This just came up. So I'm sure most people are familiar with it. NVIDIA calls it MIG, multi-instance GPU. And essentially, you're taking one full GPU and you're dividing it up into some number of smaller GPUs. And the smaller GPUs are isolated from one another. And so it's a way to sort of tailor your hardware to your actual workload. So with the Jobstats data, because we have CPU utilization and memory usage and the number of cores and the GPU utilization and memory usage and the number of GPUs for every job, we could actually calculate exactly how to divide a GPU up into the MIG instances. And so you might ask, how many 80 gigabyte GPUs should you divide into 2 40 gigabyte GPUs? You can pull the data into a data frame program like Pandas, and then you could put your criteria in and extract the jobs which could have ran on the weaker GPUs, and then you can figure out how many GPUs you should convert. And so we did this last year, and the answer was 40 in our case. And so we took 40 180 gigabyte GPUs and we converted them into 80 MIG GPUs at 40 gigabytes. And then 2 years before that, we took 8 A180 gigabyte GPUs and we converted them into 56 A100 MIG GPUs. And again, this was just based on exactly what the numbers told us to do. And this is huge. This is maybe one of the most important results in this talk, is that effectively we got a 15% increase in the number of GPUs with fewer than 10 support tickets, and we increased job throughput and we decreased queue times. So there was nothing but wins here. And it came about by analyzing the data. Okay, incidentally, a few weeks ago, we tried to apply this to our LLM cluster, but we found there was nothing to be done because their GPU utilization is fairly high and they do use a lot of the memory on the GPUs. But it worked really great on our general purpose GPU cluster. Okay, just to show you, this is what Prentice was talking about. So we can set up an alert to go looking for jobs that used one GPU and one CPU core, and their GPU utilization was less than 15%, and they use less than 10 gigabytes of GPU memory and less than 32 gigabytes of CPU memory. We can find all those jobs, and then we can send the person an email showing them how low their utilization was. And then we explain to them to please add this Slurm directive to their script so that they'll run on the lower powerful GPUs. So when you make these changes, you can announce it, but people just ignore it. But when you send them direct emails, it tends to be much more effective. And then when you run the Jobstats command line, if you ran on a MIG GPU, it will display one of these two notes at the bottom so that people understand that they're not getting a GPU with the full compute power. Okay, let's talk about detailed GPU metrics. So as Josko mentioned, he's using this GPM extension to get additional metrics about what's happening within the GPU. So we're getting the streaming multiprocessor utilization. We're getting occupancy, which is this detailed quantity or the ratio of active warps to available warps. And then we're seeing which CUDA cores are active in terms of the floating point precision. Integer arithmetic, the tensor core utilization. So this is where all the mixed precision arithmetic is happening. And basically any AI code should be taking advantage of that. And then we can look at NVLink activity. So that would be for multi-GPU jobs, or if you have Grace Hopper or Blackwell. And then also PCIe or transfers between the CPU and the GPU. So just to remind everyone, so the GPU utilization, this is the thing that you get from NVIDIA SMI, and this is reporting the fraction of a time that a kernel is running on the GPU, but it's not telling you anything about the number of threads that are running or the number of SMs that are being used. So if you know CUDA, if you do a CUDA launch and you do one block and one thread in the execution, if you're in like a while loop, you'll see 100% utilization, even though you're only using one thread out of the approximately 15,000 on an H100. There's a separate quantity called SM utilization, and this is actually looking at the percentage of SMs that are actually active. And an A100 will have about 128 SMs. And this is sort of a finer quantity to see what the actual utilization is. Let's look at a live demo. So if I go back to the browser, that job that we pulled earlier was running on in a node with H100s. And so you can see the GPU details. So now we're in the Grafana dashboard. And so I'll zoom in on one of these. So this is showing the SM percentage. And so you can see it's hovering around 50% and then it drops off. And we can compare that to the GPU utilization, which is up around like 80%. So there's the occupancy, but we're not going to worry about that. And then there's the tensor core operations. So they're down around 10%. And then the integer arithmetic. And then this is showing like the FP 32, 16, and 64. And so it appears to be quite low. Okay, and there's a bunch of other stuff, GPU memory bandwidth. And then there's GPU transfers across the PCIe bus. NVLink, this is a single GPU job, presumably, so we're not seeing anything there. So just some more detailed metric. Virginia, are you reminding me about the time?
Yes, we have 8 more minutes remaining.
Okay, we're going to just wrap up. Let's go back to notes. Okay, so what can you do with this stuff? What we're looking at is the difference between the utilization and the SM percentage. So we just saw 80% versus 50%. And if that's large, so a couple of these users have it around 30%, then maybe something can be done, but you probably have to do a detailed analysis. It's not going to be like a quick change to the code. And then on our AI cluster, we're looking out for people that have a FP64 utilization that's non-zero, basically. And then we like to see tensor core utilization. Okay, last thing in just a slide is this GPU sharing plugin. And this is being worked on by 3 people in the computer science department. And what they've realized and what we've shown is that GPUs aren't really utilized effectively, completely for most jobs. And so they're coming up with a way to schedule jobs on top of jobs. And they're starting with just interactive jobs and jobs that you want to run for testing and debugging. And they're taking advantage of unified virtual memory to try to prevent out-of-memory faults. And so this is looking promising. They've been experimenting on our cluster, and we're trying to arrange a meeting with NVIDIA and SketchMD to see if this will fit in and we can get it to work. But this is sort of where we are, is to try to squeeze more value out of our GPUs. Okay, I think we covered the summary pretty well during the course of the talk. And so lastly, we just want to thank the core contributors to the code. And I know at least I will be at PERC in July if people want to talk more there. And Josko and I are happy to continue online, but I think we have a few minutes if there's any additional questions.
I want to just remind people online, if you have a question, feel free to raise your hand, or you can type it in the chat and I'll read it aloud. And if you're in person, I think raise your hand, and I believe Doug or Sam will call on you. I'll start with Prentice first.
So not every job is going to be using a GPU right away, right? And I think you said that I think you won't cancel a job until 90 minutes in. Have you had any jobs that go longer than that before the job starts using the GPU, where you may have killed a legitimate job, and how do you deal with that?
Yeah, the answer is we have, there's 2 users. One of them's running AlphaFold, and one of them's running JAX, which does a big JIT compile. And so what we do is we just put them on an exclusion list. And so there's this excluded users flag, and we just drop them down there and just let them go.
Now, can you do that for groups? Like, say you have a whole research group that's running the same code that would be subjected to the same problem, or is it only on a per user basis?
Right now it's per user. We haven't had anybody, we haven't had any groups write in.
Okay, thank you.
And then Helen, you have the next question.
Hello. Yeah, I was just wondering, can you get information on the codes people are using? Like, can you get the stats instead of per user by per software? Say if someone wanted to look at, I don't know, CSM usage on a machine?
Sadly, we were told that if we do that, then we're breaking rules. Do you agree with that, Josko?
Yeah, I mean, we only had minimal. I mean, we had some interest in particular groups and particular usage cases where they want to do something like that. Like the LLM people may want to enrich their data by adding a comment that they can then use to post-process. So maybe they will be doing something like that in future. But overall, it's pretty anonymous as far as this thing goes. these things go. So we don't really know what they're using. So I guess it might be a really interesting application of the LLMs to try to reverse back by looking at the GPU usage and try to guess what they were running when looking at utilization. That might be fun to do.
I was just going to give a update in the sense of the way PBS collects information for all jobs submitted currently at NCAR. It does at least store the information of the scripts ran, but we don't actively parse that to identify the types of software run. But some of that information could be gleaned through those records, in a sense.
We actually do the same. Slurm has the capability of storing, and we do store the scripts, but that's considered private data. You can't query that across users. Users can check their own, and of course we can do it. But that's the scope of it. Yeah, I guess one could try to reverse, use that as well if they have a permission to do that. I guess I should mention that we had one ticket of someone who, a couple of years ago, that suggested maybe we should do the same for PBS Pro. And I even created a branch to try to parse out. I understand that PBS Pro uses C groups as well. So maybe we could collect CPU utilization data for PBS Pro, but they never followed up. So that's where it's stuck. We don't have access to PBS Pro cluster, so I don't even know how that operates. But if there is interest, we could, if there's someone who wants to work on this, we could surely modify the C group exporter to do that, as long as all the relevant C groups are present as far as the CPU and memory utilization, and the job information is present as part of the C group directory structure. It could be done, probably.
Yeah, and Daniel, I think you brought that up in Slack a while ago, right? That one of our users was asking for Jobstats functionality.
There might have been a ticket, at least specifically in Jobstats. I know I showed interest in that, I would value be able to do a lot of the things Jobstats has been doing, just our difficulty is integrating with PBS.
Yeah, okay, go ahead, Josko.
I was just going to say to not overestimate the difficulty of doing this. I mean, of course, this grew, but the basic foundation of it is not that complex. This is, I would say, apprentice knows Bill. I was always saying that you could write some of these exporters in awk. Bill is an expert in awk, so he loves doing everything in awk. It's not that complex.
Yeah, and Josko gave me access to their repo. So if there was enough interest in this, I could try doing it, porting Jobstats to PBS Pro. But I just haven't done that because I don't know how much interest there is here in doing such a thing.
Thank you for everyone who joined us today. We are at time. If you have any other questions, if we could reach out to our presenters. But thank you so much for your time today. And then I want to send a reminder in the chat. I put the CISL seminar recommendation form if you have any future recommenders. But thank you so much, Jonathan and Josko, today.
Thank you for having us. Thank you, Prentice.
Thank you.